All right, today we are starting another chapter, chapter 2 in our calculus book. And we are going to encounter our second, true calculus concept. The first true calculus concept that you encountered in chapter 1 was the idea of limits. The idea of getting ever increasingly close to a specific x value and interpreting what happened at that particular location in terms of the y value. So what we're going to do now is we're going to look at another component that we've briefly already talked about back in section 1.1, talking about slope. What happens when we're trying to find the slope of something that's not flat, right? Something that's not linear. How do we deal with that? So this is actually called the derivative in the tangent line problem, and it addresses that very issue. So we talked back in that section about secant lines versus tangent lines. And I drew you some pictures. So if these pictures seem familiar, it's because we have hit on this once before. But there's going to be some details on this that I didn't have on the picture earlier. So go ahead and sketch an axis. And we're going to do just a general curve. This is one that I use a lot. And we're going to mark a location on our curve. It doesn't really matter where. It doesn't even need to be in the same spot at all as mine, but you're just going to mark a point C. And plot the point on the curve itself. And then move some distance away and call it C plus h. So this distance is h away. And you're going to plot the corresponding point on that, at that point, corresponding location at that point. And you're going to connect these two with a line. I'm going to use a different color just so that we have a visual difference. Okay, so this looks something like that. This is called a secant line. The location along the y-axis where the first point that I marked C is would be called f of C. And then the location along the y-axis of where I marked my second point, that y value, would be in function notation f of C plus h. And when we mentioned secant lines before, we talked about the fact that secant lines are lines that sort of cut through 2 points on our curve. Okay, so I picked a point C, I picked a point a little distance away from C, I plotted their points, and I connected them with a line. That's a secant line. So when we're talking about a tangent line, what we're wanting to do is we're wanting to get close to the point or the line that we're drawing, only crossing one point on our line, at least in a nearby area, okay? So as we're taking a look at this, we're going to draw a very similar picture to what we just did, okay? And look at what happens differently when we talk about a tangent line versus a secant line. So my picture is not going to be any more perfect than yours are. Yours is. I'm going to try to mark the point C, kind of where I did before, just to give you an idea of how this works. So here's C. And my original point over here, roughly speaking, had a line, and I'll draw it back in red just like this one was. Whoops. Again, it's not going to be perfect, but it gives you an idea. That's about what I had before. That's pretty good to redrawing the same thing, don't you think? Hopefully yours looks pretty decent too. And what we did, of course, is we called this distance away h and said this is C plus h. And the question is, what if h were actually closer, or C plus h were actually closer to C than it currently is? In other words, if that h value were a little bit smaller, what would happen then? So what if instead it were actually, right here instead? And I'm just a little bit closer to C. I'm letting those points sort of get closer together. I hold one of them fixed. I'm holding C fixed. And I'm moving the point that's H away a little bit closer. What happens? Well, whoops, too much going on my screen. If I were to draw this line as my next line over here, it's still a secant line, isn't it? It's still a secant line. But I mean, let's let it get a little bit closer. What if I'm over here instead? I can draw the line again, right? So now my line looks more like, give me a second, I'll move it, because like this. And then what if, I get a little bit closer even, and I feel like I need to change colors because now that I'm overlapping everything, it's hard to see what's going on. What if their point right here is the blue point? Can you see that blue point that I marked? Well, how does it look like then? Well, that line, again, adjusts slightly, ever so slightly, and I'll draw mine in orange this time. And now it's getting closer and closer. And it gets closer and closer to looking like it's only going to cross that one particular point at C, because the distance between my 2 points is getting really, really small. And that idea of narrowing the gap is the same idea that we had when we talked about limits, right? The idea of getting ever increasingly closer to a specific point is happening again. But now we're talking about it in terms of what's happening to the curve, the slope of the line, instead of what's happening to the y value at that particular point. So you'll remember when you find slope, there's lots of formulas for it. One of them looks like this, y2 minus y1 over x2 minus x1, right? Does that look like a familiar form of the slope equation? Okay. So what you do is you take the two y values and you subtract them on top. So here's my secant line slope, right? There's the first one of the y values, f of c plus h. Here's the other y value, f of c, and we're subtracting them. And then I have my two x values, x2 and x1, right, which are c plus h and c, and I'm subtracting them on bottom. And the lovely thing, of course, on the bottom is that when I subtract them, the c part goes away and I'm only left with h. So the slope for the actual secant line is just f of c plus h minus f of c over h. And then you can sort of evaluate how close you want to be. Well, how close do you want to be? What c value am I trying to find? Is it the c value of 5? Okay, fine. We'll put 5 in for c. How far away do I want to be? Well, maybe I want to be 0.1 away. Okay, then the h's are all 0.1. And I use 0.1 in that value. So c's and h's here are variable quantities, right? The c is fixed. I'm going to have to choose it. But then the h is going to change depending on how close I want to get to the particular point I care about. So as we sort of let the h value get ever increasingly, not h, but c plus h, get ever increasingly near to the c value I started with, that's actually a limiting process. So if you take a look at that same equation, not equation, but expression, it's right there. Do you see it? F of c plus h minus f of c over h. It's still in there. The only new thing here that we didn't have before is this limit part at the beginning. So let me read this with you so you can have a feel for what's going on. It says if f is defined on an open interval containing c, and if this limit, right, this slope value exists, and we'll talk about, I think it's at the end of this lesson. Yeah, we'll talk about where that doesn't happen. There are some places where that doesn't happen, but for the moment, most of the things we deal with are going to work. Then the line passing through C, f of c with slope m, is the tangent line, right? It turns into the tangent line of the graph of f at the point C, f of c. This slope of the tangent line to the graph of f at the point C, f of c is also called the slope of the graph. So this is really important because there's going to be several words that all mean the same thing, and they're going to be used interchangeably. And we do this, unfortunately, a lot in math, where there's lots of language pieces, and you just have to know that it's talking about the same thing. For example, if I talk about a square root and I talk about a radical with index 2, those are exactly the same thing. One of them is when we talk about more frequently, we use the language more consistently. You've heard square root probably far more than you've heard the word radical. It's not that you've never heard the word radical, but you've heard the word square root, the phrase, much more frequently. But they mean the same thing. So this is another one of those places. So if you take a look, we've got several pieces already. This one says slope of the tangent line, and this one says slope of the graph. Okay? And we will add to this description in a little bit with another phrase. But these are the two phrases right now, the slope of the graph and the slope of the tangent line. Okay? So we're going to do an example so you can see how this actually plays out, where we've got a curve. And it is a curve, like a legit curve, not a line that I'm sort of using the general phrasing of curve for, right? This is not a line. It's 6 minus x squared. So when we went back to section 1.1 and they were asking questions like, do you need calculus or pre-calculus to do this? You absolutely need calculus to do this because it's not a line, right? There's no standard slope on this thing. And we're going to use this idea that we've just developed of letting this space between my values get ever increasingly closer together. Now, the lovely thing about this is that they actually give you not only the x value, but they give you the y value. Not that you couldn't find it, right? If you're given an x value, you could plug it in and find it. But it's just one less thing to have to do. All right, your textbook, for whatever reason, really likes to give you both the x and the y coordinate. So yay for you. Not all textbooks do that. So it's just one less thing to deal with. So in terms of like your x value and y value for slope, this would be the x1 and the y1, right? Or this would be the c and the f of c plus h if you're using our other notations. The c, and then this is f of c. We're about to get to the plus h's. Sorry, I misspoke there. Okay. So this is always going to start out the same. You're going to start out by writing down the limit as h goes to 0. And just like when we did all of our other limits, until we actually plug 0 in for h, we're going to write this every single time. And again, it's like having a square root, right? If you have the square root of 9 plus 3, right? You don't just stop writing the square root until you actually take the square root of the thing. Square root gets written every single time until you actually do that operation. So a limit is like an operation, okay? We don't remove the notation until we actually accomplish that part of the notation. So what are we going to do? Well, let's take a look. The first piece says that I need to do f of c plus h. Well, my c is 1, so c plus h would be 1 plus h. So I'm just going to write down what I have. I need to do g of 1 plus h. Okay? I realize I haven't actually done a whole lot. I've just written a piece of my puzzle here. But I'd like to get all the pieces written in so that we know where we're going before I just start evaluating stuff, because then it starts getting confusing. The next thing it says that I'm supposed to do is I'm supposed to subtract f of c. And again, my f has the name g. I don't care what letter you use. Use f, use g. That doesn't matter. But my c value here is 1. So I'm going to subtract off g of 1. Okay. And then I'm going to divide by h. Eventually, I want to plug 0 in for h, but obviously I can't right now, right? Give me a 0 in the denominator. So one of the ways in which we've done limits, and we've talked about them, is if it's possible, and you can just plug numbers in, we want to do that. That's called algebraically or analytically finding limits. And as we're looking in this particular section of this chapter, that's our focus. Our goal is to do all the algebra so that eventually we can plug in 0 for h. Okay, that's our goal. So if you'll remember this notation right here, it's function notation. It means that I take my function and I replace my x with 1 plus h. So right here, it needs to say 1 plus h. So I'm just going to write this over to the side as a reminder step. When I'm doing this g of 1 plus h, it means that I'm going to have 6 minus 1 plus h squared. So if you want to do the algebra to simplify that as a side step, that's okay. You don't have to. But it's going to be there whether you do it here or later. So right now I'll put it in brackets, 6 minus, and I have 1 plus h squared. And what I've got in those brackets right now is the part that I've highlighted above in pink. Everything here is this. Okay? They're the exact same thing. Now I have another piece, of course. I have this piece over here that says g of 1. So g of 1 right here that I've highlighted now in the green means, again, I take the equation that's g, and I evaluate it at the x value of 1. So this is 6 minus, and then it's just 1 squared on that one instead of 1 plus h. Okay? Those are algebra steps. There are several algebra steps all combined, but that's just algebra.
Since it gives us the y value, do we need to show it?
You wouldn't have to. You could put the value there. Yeah. They don't always, let's say your book often gives you the y value, but in what we're working on in general, it won't always be there, so you wouldn't necessarily do it. So what Jeff's saying is that this is going to end up being 5. And he knows it because they told us it right here. Do you guys see that? So do I actually have to write it out? No, you could just put a 5 in there. It'd be okay. All right. And then we're going to divide by h. So when we get it all written down at this point, it's just a bunch of algebra to simplify. You need to be a little careful, right? Because the negative sign throws everything off. So you mess up part of the algebra and you're going to find yourself up a creek very quickly. Because eventually what should happen is that h in the denominator should cancel with a factor of h in the numerator. And if that doesn't happen, you have an error somewhere, right? So let's actually do some of this algebra to simplify. So this is 6 minus. So 1 plus h squared, remember, actually let me write this over to the side just to remind you. This piece right here means 1 plus h times 1 plus h. You don't just square the 1 and square the h, right? That's a no-go. That's not going to work. You have to FOIL it out or distribute it out. So as we're thinking about that, I'll still leave it in a parenthesis. But I'm going to have 1 plus 2h and plus h squared when I distribute that multiplication out. And then just like Jeff said, this would then be minus 5 at the end, because my 6 minus 1 squared, it'd be 5. And also I was given that. It's all over h, but I still haven't actually plugged 0 in for h, so I will still keep writing limit as h goes to 0. Everybody good so far? You do need to be a little bit careful on this one because the negative, of course, applies to everything inside that parenthesis. So I have 6 minus 1. I'm going to go ahead and write that as 5, just to avoid rewriting one more step later. And then I have negative 2h, negative h squared, and minus 5. And lo and behold, what wonderful thing am I about to be able to do? Tell me something wonderful. Not yet. That's the next thing. There's one thing before that. The 5s. Thank you so much. You bet. Right? This 5 and this 5, they add to 0. And because those add to 0, is it Reed? Is that right?
Yes.
Okay, I'm working on names still. So Reed's right. The next thing after the 5s go away is to notice that everything has an h in it. Do you see that? Mm-hmm. So that actually lets us divide each component by h. Now you have to make sure you are careful with that, right? H divided by h here is 1. H squared divided by h here is h. And h divided by h in the denominator is also a 1. They don't cancel to 0, right? They cancel to 1. So in the numerator, I'm left with negative 2. Minus h, and in the denominator I have a 1. You can write it if you wish, but of course division by 1 is the same as what you already had. And that really was my goal. My goal was to get the h in the denominator to cancel, because it was the reason I could not get rid of the limit notation, plug in h as 0, those kinds of things. And now that I have, the h will actually be able to be evaluated at the point 0. Right? Negative 2, minus 0, and I get a value of negative 2. It's good news. Now here's the bad news. That only works for the c value of 1. If they give me this problem, and then in part B, or whatever, they say, now do it when c is equal to 2. We've got to start way back at the very beginning and rework everything, because that c value was what forced everything to happen afterwards. It's what determined all of the values within the problem, right? So that c value being the number 1 here was really important to actually being able to work this problem out. So what would happen if you were given, a 5-part problem and it asked you, you're not going to be given a 5-part problem, but what if you were, right? What if you needed to do it multiple times and you're like, dude, I really don't want to do this 5 times. That sounds like awful. And it would be awful. You'd have to rework all the algebra every single time. So what do you do instead in order to avoid having to rework the problem every time? Well, what you can do is you can do it in general for any x value, so that at the end, you're able to simply plug the x in at the end instead of at the beginning. And when you do that, you're actually working out a problem that's called the derivative. Okay, so we had 2 words already that meant the same thing: slope of the tangent line and slope of the graph. This is the third item that means the same thing, the word derivative. So we now have 3 different phrases meaning the same thing. You'll notice everything here looks the same, except instead of having c's here, we have x's here. And you might think, so what? You changed a letter. What difference does it make? Well, conceptually speaking, c was a number and x is a variable. I mean, I don't know what c is, but it was a number that we were using to evaluate it at. And now I'm using the variable x instead. And you'll notice a new notation as well. the notation is this prime notation. So f with we call it f prime. And it denotes the derivative, slope of the graph, the slope of the tangent line. All the same thing. All right, so what do we do differently? Well, if you take a look back over here, I'm going to go back to our problem where we did it. Everywhere where I had a 1 in that very first line, in particular here and here, I wouldn't have a numerical value of 1. I would have had an x. And as I worked things out, things would still cancel out, but they wouldn't cancel numbers out. It would cancel variables of x out as I worked. So we're going to do an example, of course, to see what that looks like with a different type of function. And I showed you one. The first one was it was a quadratic specifically, polynomial in general. But I want to show you that it works for other types of functions too. So this is a rational equation, right? And we're going to see how this works. So the starting point is the same place. I write limit as h goes to 0. Okay, that's how it's always going to start. If you wish, you can actually give this a name. This is going to be f prime when I'm done. I didn't have that notation before to write down, so I could write it here if you wish. Okay, so what the derivative, the previous slide right here, what the definition of derivative said is I need to do f of x plus h minus f of x over h. So I'm just going to write that in. So this step right here will look exactly the same on every single problem. F of x plus h minus f of x over h with the limit notation at the beginning. Okay? If you've had any calculus course in the past, you know, real quickly, that I'm about to show you shortcuts in another day or two. But right now, this is all you know. So pretend like you haven't seen any shortcuts. Okay? I've had several of you in my office at this point and so forth, so I know that some of you have been through this before. Right now, all you know is this definition. Okay. All right, so what do? Well, we do the same thing we did before. I have to change each of these notations and put them in as what they are for my function. So my function is 1 over x squared. So instead of saying 1 over x squared, it's going to say 1 over x plus h squared. Now the cool thing is that because I'm not evaluating at 1, this actually looks exactly like it began with. Right, so this notation here at the end is just exactly what I have right here. It is 1 over x squared. And then, of course, all of that's divided by h, and I know fractions inside of fractions are not the prettiest thing to look at. So we'll get that cleaned up pretty quick with the limit notation at the front, because I still have h in my problem. I have not evaluated it at the point 0. Okay, so far so good? So it feels a little bit like I'm just doing some manipulation of symbols at the moment, and I understand that. But it's algebra manipulation, and you know how to do your algebra, or you wouldn't be in calculus. All right? So we need to rewrite this x plus h business that's squared, much like I did on this problem over here when I had 1 plus h squared, right? I still have to multiply all that out, FOIL, distribute, whatever phrasing you want to use. So I've got the limit as h goes to 0. 1 over, and then if I had x plus h times x plus h, right? I'd have x squared plus 2xh plus h squared. I still have minus 1 over x squared and 1 over h, and all over h, excuse me. I'm going to pause right here. How are we doing? Any questions about where any of those pieces came from? Definitely now's the time to ask. Okay. What is like the overarching most important thing about adding and subtracting fractions that makes it possible to do? Gotta have a common denominator. And common denominators have to have the same factors in them. So I can't just look at it and say, hey, they both have an x squared. Well, they do, but in the first denominator, it's x squared plus something. So it's like, it doesn't count. It's not a factor. It's a term. It's a part of something that's being added together. So it doesn't help you that they have an x squared in common because they're not in common in the right way. Okay, so what do you do about that? Well, Unfortunately, that means they don't have anything in common because the second denominator is x squared all by itself anyway, yeah? So in order to add these together, they have to be multiplied by one another. So this one will get multiplied by x squared over x squared. And this one will get multiplied by x squared plus 2xh plus h squared over x squared plus 2xh plus h squared, all of it. Okay, that's going to get my common denominators. I promise we'll eventually get rid of that double fraction going on. We're not that far from being able to do it, but we're still not there quite yet. So the beautiful thing then, of course, that is by doing this, the denominators will in fact match. Agreed? Yeah, they will. They will both have the same denominator, and I do not want to multiply it out. That sounds terrible. All right, we're going to leave it in factored form. Factored form is so much friendlier because remember, our goal eventually is to cancel something out. So I'm going to, and plug in lots of zeros for h's, and zeros from h's are going to make things go away too. So I don't really want to clean things up by multiplying it out. That won't help me. And my first numerator is x squared. My second numerator is subtraction of all of this, right? So it's minus x squared and minus 2xh and minus h squared. There's still something I haven't written. What's missing from my notation right now? I think some of you are seeing it. You just don't want to talk to me this morning. It's Monday, right? What's missing? The over h. You bet. This piece right here. I haven't put that back in yet. And I told you just a moment ago we really would like to not have double fractions. I've said it at least twice now. But division by h is the same as multiplication by the reciprocal. So what's the reciprocal of h? 1 over h. So there's my reciprocal, and I don't have double fractions now. And I'm only able to do that now finally because I have a single fraction on top. When I had two fractions being subtracted on top, that's not helpful, right? I mean, that made the notation messy. So I'm able to multiply by the reciprocal once I've combined those two fractions together. So let's take a look at what are some of the things that we see that cancel out, add to 0. What do you see?
Those top two x squared.
You betcha. Good job. So the x squareds here, add to 0. And once they're no longer there, right, so cover them up, pretend like you don't see them. Do you notice that you have h's in each of the pieces that are still left in the numerator? Yeah? That's good, because that's the only way I'm going to get this h over here at the end that I just made the reciprocal 1 over h, that piece, to cancel out. Okay? So if you need to write it together to see that, that's okay. But if you can see it right here, that's great too, that I've got an h here, and an h down here. So I'm able to actually reduce those as well. So this h would divide out to being 1, this h squared would become h, and this h would become a 1. Okay, still haven't dealt with my limit problem, so limit h goes to 0. Somebody help me out. What am I left with in the numerator at this point? I've canceled a bunch of stuffs, so what still remains? Negative 2x minus h. Is that good for everybody, for my numerator? Yep. And the denominator in factored form still looks like x squared times x squared plus 2xh plus h squared. And remember, the whole problem with the plugging in h for 0 was this h over here that was the 1 over h now being in the denominator. That was the problem, truly. And once I canceled that h in the denominator out with the h's that appeared in every term in the numerator, I no longer have a problem evaluating at 0. So I can plug in zeros for all my h's. So in particular, if 0 is in this h, this whole thing becomes 0, right? The 2xh will all be 0. And the 0 in for this h makes the h squared become 0. And so when we're taking a look at what remained, oh wait, and one more, this h right here on the numerator also becomes 0. You see all those zeros that turned around? And again, the same reason. I mean, this is why I don't want to evaluate, like FOIL everything out, like distribute everything. I don't need to. Most of them are going to go away. I don't want to deal with them any more than I have to. So when I plug all of that in, I have negative 2x on top. What do you have on bottom?
4 cubed, x cubed.
X, close. X to the 4th on bottom.
That's
that what you meant? Okay, yeah. So there's this x squared and there's this x squared. So that gives me x to the fourth on bottom. But take a look at then what I have. I have 2x on top, negative 2x on top, and x to the fourth on bottom. So what else can I do then? I can take out an x, right? I can simplify that down. So this x divided by x would be 1. This x to the fourth divided by x would be x cubed. So what I end up with at the end with, my f prime, right, my derivative notation, is I have negative 2 over x cubed. Yeah, so now if I was in that case that I mentioned before and they wanted me to know, well, what happens when c or x is 1? I can just plug it in here and I can give an answer. Well, what happens if it's 5? Well, I just plug it in here and I give an answer, and I don't have to recreate this entire limit process for every individual value of x that I'm given. I can evaluate it for multiple values of x very, very quickly with only doing the limit process one time, and that's super beneficial. All right, because this one in particular compared to the last one, this is a lot more work, right? That common denominator business and everything, it creates a lot of problems, at least a lot of work. Okay, so we've done a polynomial. Polynomials are the simplest ones to do limit definitions for. There's algebra involved, but the algebra is pretty clean. We've done a rational, right? Rational ones have to have this issue of combining like terms with, or getting common denominators to combine the fractions together. And we're going to do one more that's similar. The directions are slightly different, but let me just talk about the function now. The reason I'm choosing this function is because it's not a polynomial and it's not a rational. So I want you to see what happens when we have a radical. Okay? Now the directions change just slightly. The directions here say to find an equation of a tangent line to the graph and then to use your calculator to verify that it makes sense. Okay? So starting with equation of a tangent line, let's just look at what it means by to say an equation of a line. Do you guys know a general equation of a line? There's multiple options here that could be right. Say it for me, Lally. Right? Okay, so y equals, right, mx plus b. Nod your head if that looks familiar. Okay, should. This is one that probably dates back to somewhere around 6th or 7th grade where you learned it. Okay, so you've been seeing this for a long time. M is your slope, yes? And remember, slope is exactly what we keep finding. Slope of the graph, slope of the tangent line, slope, slope, slope. Everything we're doing right now is all about finding slope. It's a big component. In fact, we're going to kind of like settle into this issue of slope for 2 chapters. Chapters 2 and chapter 3 are all about slope. Different applications, but all about slope. So we're going to find this slope of the tangent line because we actually have an equation that we can use to find the slope. Like all that goes together. The b value, we'll talk about how to find that, and we'll be able to use that in a moment. Okay, but we're just going to find the slope right now, just like we've done before. So how do I find the slope? Well, the slope, which is the same thing as f prime of x, right, is this limit definition business. The limit as h goes to 0. And I'm just going to write it out first as a reminder, f of x plus h minus f of x over h. Okay, but my function now is a radical function. Okay, so what do? Well, it means that where I have that notation that says f of x plus h, this x now needs to be x plus h. So instead of just having the square root of x, I've got the square root of x plus h. And then I've got the function notation here at the end, f of x, but that is exactly what I'm told. It's just square root of x. And all of this is over h. We've seen problems like this before, haven't we? A radical, and they're in the numerator, and I'd like to plug something in the denominator that I can't. This is not the first time around this. We've done this several times in class, actually, and you've done on your homework, too. What was the phrase that we used in order to actually change this numerator so it didn't have radicals in it? Conjugate. We actually multiplied by the conjugate. And the conjugate means the exact same thing that's in the numerator, but the sign between the two pieces of the numerator is the opposite sign. So we're going to multiply by the square root of x plus h, and instead of it being minus, it will be plus the square root of x. We're going to do it on the numerator, of course, and the denominator. These are fractions. Whatever you do on top, you have to do on bottom. Okay, so as we saw before, the beautiful thing and the whole purpose and the reason behind why we're doing it is because when I multiply these two pieces in the numerator, all the radicals eliminate themselves, right? They cancel out. So I end up talking about getting the square root of x plus h times the square root of x plus h. And when you multiply a square root by itself like that, the square root is eliminated to give you simply x plus h. The other half of it, right here, the square root of x and the square root of x would give you minus x. And again, we're not interested in distributing and cleaning up, quote unquote, the denominator. It really makes it more of a mess. We're interested in leaving things factored. So everything just looks the same in the denominator as it already did in factored form from the previous step. I still haven't plugged in the h is 0, so the limit as h goes to 0 is at the beginning. And there's where I am. What wonderful things happen. Yep, the x here and here add to 0. Yeah, and this is where I want you to be really careful, right? Because when you're canceling h's, you have to recognize that you're canceling it means division, right? This is dividing by, so I'm dividing by h, which leaves me with a 1 here and here. So I still have 1 in the numerator. This did not become 0 in my numerator. And I still have a 1 in the numerator. And the denominator, I have square root of x plus h plus the square root of x. And my limit notation. But the h that was originally in the denominator has now become a 1. Right? The h is not there causing me problems anymore for evaluation purposes. So I can actually plug the 0 in now for h. And that's great. That's where I wanted to be. So now I have 1 over square root of x plus the square root of x, because h is 0. So that looks a lot like 1 over 2 square root x. You don't like that. That's okay. That's the slope. At least it's a general form for the equation of a slope. But we actually do care about a specific slope, like a specific point to find the slope at. What's the point where we care at this particular problem? Yeah, it's at 1, 1 up here, right? X is 1, y is 1. So what I really want is I really want to take, so here's my function that I just found, f prime of x is equal to 1 over 2 square root of x. But what I really want is I want to find f prime at 1, because I was told my x value is 1, right? And that's beautiful, right? What's the square root of 1? 1. So what's the slope? 1/2. So here's what I have now. I have a slope of 1/2, and I have a point, at 1, 1. If you have a slope and a point, you can find that b value. There's a couple of things you could do. If you want to remember, there is another form of a line that might be useful to you. Y minus y1 equals m times x minus x1. It's called the point slope form of an equation. You can plug in x1, you can plug in y1, you can plug in m, and you can move the numbers, and you can get it all nice, neat, and pretty. That's fine. The other option, if you'd like, is you can take, and I'll show you this in case some of you have never seen this before, because not everybody does. You can take that y equal mx plus b. You can plug in y equal 1. You can plug in your m equal to 1/2 and your x equal to 1. And you can simply solve for b that way as well. Okay? I'll continue this one since this is the one I started. So if this is 1 equals 1/2 plus b, what's b? It's 1/2, right? Because 1/2 plus 1/2 would be my 1. So my equation would be y equals 1/2 x plus 1/2. And if you don't like what I just did with the solving for b, that's fine. Use the other point slope form of the equation, you'll get the same thing. This is part A. Part A said to find the equation of the tangent line. Grab your calculator real quick. Here's what I want you to do. I want you to put the original equation in your calculator, f of x equals square root of x, that's in y1. And your answer that we just got down here, 1/2 x plus 1/2, make that y2. I don't have this one drawn in my notes, so let me put it in with mine. to be able to see the same thing you are. If you're wanting to know, like, well, what window do I pick? It doesn't really matter that much. Just a standard window is fine, like zoom 6. A 10 by 10 window, if you want to zoom in a little bit further, that's fine too. What we care about is what happens near the point of x equal to 1, of course, because that's the whole location at which we found all of our values, right? And if you zoom in, you get something that looks, this is my square root graph, looks something like that. And if you zoomed in enough to actually see, what you would actually end up seeing, especially if you have the colorful ones, because some of you have these calculators that graph in colors, which is fantastic. Mine doesn't do that, it's old. But you actually see that there is a location where it's simply touching the side of the curve like we anticipated happening, which is pretty cool. Okay, so that's how you can verify. Part B is actually asking you to verify. I know some of you are struggling with the Flash player on your My Math, or not My Math Lab, but your WebAssign stuff. You should be able to be using that on a non-Mac. I'm still struggling with, I might have a Mac as well. For those of you who have a Mac, you're probably having the same problems I am. And I haven't gotten any response from WebAssign about what to do yet. And I've tried it multiple times with Noah, actually. So switch to somebody else's Dell or Toshiba or whatever they have that's not a Mac, and you should probably be okay. Yes, sir.
What kind of computer do you have?
HP.
Your HP didn't like it either? Did your Dell work okay? Okay, somebody's are working okay, because some of you are not having problems.
A little piece on the side that has the flash power
Yep.
player. By default, it wants you to ask, and sometimes it doesn't ask, so you have to hit. So click on that, and it'll drop down a menu, and it says allow, and press allow, and refresh.
Okay.
I tried doing that and it
It's still fussed at you?
Yeah, and I tried to like download
Flash
it.
player. You're completely.
I have absolutely no idea. Where did you hear that?
It popped up on the flash player for me.
It popped up, so yours is working fine. Okay.
I know with the Mac, all I do is go to my system preferences and I just allow it now.
Yeah.
There's also
Okay.
a little lock icon, like where you put the website.
Okay.
you send, and you click on it. And I forget
Yeah, that's what's happening.
but there's like a little drop down that says allow. plugin.
Okay, so try some of these options, see what you can do. I will do the same in my computer and see if I can get it to, finagle mine as well, because I also cannot see what you guys are, I know what you're having problems with because I can't see it too. So play around with that. There's a couple more things I want to do real quick with you on our last page here. These are super fast notes. I mentioned that there are places where the derivative doesn't exist. That was the very first definition thing. It says, if it exists, if the limit exists. And I said, there are some places where it doesn't exist, and these are the locations. Discontinuities, so if we have holes or jumps, we will not have tangent lines. So if there is a hole or a jump, there's no tangent line. And if you kind of imagine that, obviously if you have a hole in the graph, you can't talk about f of c. It doesn't exist, right? If you have a jump in the graph, you can imagine too, what's happening is you potentially have slopes that are different on either side of them. That's obviously a problem. Sharp turns don't happen all that frequently, at least in most of the functions we deal with. But if you have something that looks like this, you got a problem, because the slope on one side looks like, this, right? And the slope on the other side looks like that. So what happens in between? What do you do? Okay, so that slope doesn't exist. And the last one, again, also doesn't happen. None of these happen real frequently, just FYI, but they are legit, honest problems, is if you have a vertical tangent line. So if you were to have a vertical line as your tangent line, the tangent line most definitely exists, but the slope does not exist there. We call that an undefined slope, okay? So the slope or derivative would not exist at a vertical tangent line. Here is something interesting. We talked about continuity back in chapter 1 at different points, right? This idea of, the general idea is the idea of, can I draw it without picking up my pencil, right? And we talked about certain functions are automatically continuous and other ones maybe aren't if they've got denominators that equal 0 and things like that. But if you have something that's differentiable, it is automatically continuous. The other direction simply isn't always true. If it's continuous, it is not always differentiable. And if you're not sure about that, take a look back at number 2 and number 3 that are back on this other slide. 2 and 3 were both continuous. They were not differentiable at those two locations. Okay? Last example. Describe this x values at which f is differentiable. There are ways in your calculator to get this to graph. If you don't know them and you want to stay after for just a couple minutes and make sure you can see where they are in your calculator, feel free to do that, or to the Success Center. But there is an absolute value function where you can tell your calculator like y1 equals ABS. Some of your higher calculators that aren't my functioning actually put the absolute value symbols on there. And it will graph this, but let me show you what it actually ends up looking like so we can talk about how to think about this when we are asked a question about the absolute value and we're given the graph or need to find it from there. If you graph this, it looks like this. Didn't get that going far enough. That's terrible. It looks like a W, yes. Okay, that's not too bad. So it looks kind of like a W like this. And the question simply asks you to describe the x values where f is differentiable. Now notice how it asks it in a positive way. When does it work? And we always look at when it doesn't work to give the answer. So my first question to you is not going to be the answer to your question. It's going to be the exact opposite. When is it not differentiable on this picture? What x values? 3 and -3, yeah. At this value of 3 and at this value of -3, there are sharp turns. So what we really identify first, it is not differentiable, and I just abbreviate it DIFF, at 3 and -3. So how do I write where it is? Well, I write it in interval notation, because that's actually the question I'm asked, is that it is differentiable. Well, yeah, -infinity to -3. Your program probably puts a U here. -3 to 3. And then 3 to infinity. This is more basic algebra, though you may not have seen the interval notation in a while. Anytime you have infinities, we use parentheses. And anytime we're not allowing ourselves to equal the value, which is exactly what we're doing here, we don't want to equal 3 and -3, we use the parentheses. The U's between are the word union. They simply mean that it includes all those pieces as potential places where it is differentiable, right? Everywhere that's not 3 and -3, it's smooth. There's no sharp turns. There's no vertical tangent lines. None of that's happening, so we're good to go. All right, so you have web assigned homework that is due on Wednesday before class, and we will move on into section 2.2 at that time.